Example 5.3.5. This one says you have two different investment opportunities you are trying to choose between. Each requires an initial investment of $10,000 and will repay the investment plus interest after 5 years. Investment A offers an APR of 5% with daily compounding. Investment B offers an APR of 5.1% with annual compounding. Which investment offers the higher payout 5 years from today? Okay, so we have two pretty similar investments here. Both will put in $10,000 today and will get something back 5 years from today. They have slightly different annual percentage rates, APRs, but they have very different compounding frequencies, right? An APR is the annual percentage rate or the amount of interest that, in this case, we're earning every year, but without the effects of compounding. And so there's going to be a pretty significant difference between daily compounding, which would be 365 times over the course of a single year, versus annual compounding, where we're only going to get paid interest once per year. There's going to be a lot more interest on interest we're going to pick up with daily compounding. So it's not clear from the outset which one of these is going to offer a higher payoff. Just because the APR is higher on the annual compounding investment does not necessarily mean that it's going to have a higher payoff, because it compounds less frequently than the other investment with a lower APR. So we have to actually calculate these guys to see which one is going to be better, offer a higher return in the end. And so we're going to follow our three-step process. We'll start by mapping the cash flows out so that we can be sure what we're dealing with here. All right, and let's say this is investment A. With investment A, we're going to have a cash outflow today of $10,000. We adopt the perspective of the person making the investment. And then this guy isn't going to make any payments. The value is just going to sit there, but it is going to be credited interest every day. So the compounding frequency with this one is daily. So this first tick mark means one day after making the investment. The second tick mark is 2 days after making the investment. And then that is going to keep happening for 5 years. So we have to figure out how many days are in 5 years to figure out what the last tick mark is on our timeline. And we can do that by taking 5 years times 365 days per year. And that is going to be 1,825 days, or we're going to get paid interest 1,825 times over the course of this investment. And what we want to know is, what is the payoff going to be? So 5 years from today, when we get our principal amount, that $10,000 back, plus the interest that they promised to pay us, how much are we going to get? That's a value at the end of the timeline, just a lump sum value at the end. That's going to be future value that we're looking for. Our interest rate that we use here, the rate that we use to evaluate this investment, needs to match the frequency of the compounding periods. And so with this one that's daily, we need an actual daily rate on this guy. And we can figure that out with our APR definition, where APR is defined as little r, which is the periodic effective rate that matches the compounding periods, and then m, the number of compounding periods per year. With investment A, we know it's a 5% APR. We're looking for a little r, and we know there are 365 compounding periods per year. All right, so we want to solve for little r. We'll just divide both sides by 365. And I'll flip r over to left here, since that's how we're used to looking at things like that. So 5 divided by 365 is 0.0137. And I started with 5 in percentage terms, so that is in percent format. That's 0.0137%. Okay, that's all the information for investment A. We're just going to invest $10,000 today. It's going to earn interest for 1,825 days. And each day, we are going to earn 0.0137% interest on that $10,000. All right, so step 2. Well, let's just go ahead and map out both of these investments, actually, since they're going to be the same type of cash flow. So investment B, then, is going to look pretty similar. With investment B, we're also going to make a $10,000 investment today, so that'll be a cash outflow for us. And this guy is going to earn interest over 5 years, but in this case, we're only going to be credited interest once per year. So our number of compounding periods, our total number of compounding periods, is only going to be 5. And we still want to know what the future value of that 10,000 is after 5 years. And our R, in this case, it's already, the compounding frequency is annually, the APR is an annual rate, so our R is just 5%. And just for the sake of seeing it, let's go ahead and walk through that same, we'll use a definition of APR to calculate the correct periodic effective rate, because that can easily be confusing that we're plugging in an APR here, and we've never done that before. Well, here's why. This is actually little r. It just happens to be the same value as the APR in this case because, oh, and it's 5.1%, I'm sorry. If we look back up at the problem, investment B has an APR of 5.1% instead of 5%. It's slightly higher. All right, so our APR is 5.1%. Little r is what we want to solve for. And the M is the number of compounding periods per year. Well, in this case, since we're only getting credited interest annually, M is 1. And so to figure out what little r is, we need to solve for it. So we'll divide both sides by 1. Well, 5.1 divided by 1 is itself. And so our little r, our periodic effective rate, is also 5.1%. And that's because we only have one compounding period per year. So in the odd case where we're looking at annual payments or annual compounding periods, then the APR is an accurate measure of the interest you're actually earning because there is no compounding happening within the year. So it doesn't matter that the APR excludes the effects of compounding within the year. Okay, so these cash flows, we've got a single cash outflow at the beginning of the timeline and a single cash inflow at the end of the timeline. These are lump sum cash flows. And if we look at our cheat sheet for lump sum cash flows, we've got 3 tools available for those. We've got the present value, future value of a lump sum formula, and which one we would use would just depend on what information we're given and what we're solving for. In this case, we're looking for future value, so we would use the future value of a lump sum cash flow. We've got the time value money keys and a financial calculator, and we've got a spreadsheet that we could use. As always, we're going to sidestep the spreadsheet because we generally will not have access to that on an exam, and we are preparing to do well on assessments in the course. The formulas for lump sums are relatively straightforward, and frankly, if I'm working a lump sum problem, I tend to reach right for the formula, and I won't even use the calculator most of the time, just because the formula is relatively easy to use, and there's fewer opportunities to mess something up as compared to like the present value of an annuity formula. With the other problems in Chapter 5, though, we've been going straight to the calculator, so we'll do the same thing with this one. Step 2 is to identify the type of cash flow. We figured out that they were lump sum cash flows. And then step 3 is to select the appropriate tool, and we're going to go straight for the time value money keys on the financial calculator. And we'll look at each one individually. Investment A, we'll set up the keys on the financial calculator. I like to write them vertically in the same order that they appear in the calculator. You're welcome to use whatever format you want. I just encourage you to actually write them down and also to come up with a strategy that you use, a method that you use the same way every time, and that helps prevent missing information along the way. All right, N for investment A. N is the number of compounding periods over the life of the investment, and that's going to be the number that's above the last tick mark on our timeline. We're going to be credited interest 1,825 times with this investment, so our N is 1,825. Since that is in days, that's 1,825 days, our I over Y needs to be the daily effective rate, which I know we've already calculated here. It's still on the display. But instead of writing in that 4 decimal approximation, I'm actually going to write here 5 divided by 365 to remind myself that I want to actually have the calculator do this division and then store the calculated answer instead of typing in that 4 decimal approximation. Present value is going to be a cash outflow of 10,000. What we put on the present value key is what happens at time period 0 on the timeline. And for investment A, that is a cash outflow of 10,000. What goes on the payment key are any cash flows that happen over and over again, so at each tick mark on the timeline. Well, this one we don't have that. We don't have payments. If we did, we'd be looking at an annuity of some flavor. So we're going to put in 0 there for payment, and future value is what we're looking for. All right, so let's go ahead and enter these guys in. I'm going to start by clearing out the time value money keys because the last problem I worked is still in there. And when I hit clear TVM, it records 0 on all those keys. And then I'm just going to work left to right. N is 1,825, so I'll type that in and then press the N key to store it. I over Y is 5 divided by 365 equals. And now, although the calculator is showing me 4 decimals here, because it's a calculated value, it's worked out to about 13 decimal places. And if I have the calculator do that division, and then while this number is on the display, I press the I over Y key, it stores that full 13 decimal version of the answer instead of that 4 decimal approximation. And if we look at the formula real quick, we're calculating future value here. That N is the total number of compounding periods. That's 1,825. So any rounding error we introduce here at R by using a 4 decimal approximation instead of 13 decimals is going to get magnified exponentially 1,825 times. And our answer could be fairly different than what we would get if we were being more precise. We want to be as precise as we can when we've got N's this big for sure. All right, present value is a negative 10,000, or a cash outflow of 10,000. Payment is 0, which it should already be since we cleared it out. But I'm going to go ahead and type 0 and then press the payment key to store it. And now we've got 4 of the variables stored. The calculator can solve for the 5th, and we do that by hitting Compute FV. All right, so with investment A, when we invest $10,000 today, 5 years from now, we will receive $12,840.03. So if we were to put that on our timeline, that's going to go up here. We'll have a cash inflow of $12,840.03. Okay, let's do the same thing for investment B that has that slightly higher APR and see if we get something different. So same setup for B. We'll write out the calculator keys. And in this case, I'm actually, I'm not going to clear it out. That present value is the same amount. The payment is the same amount. It's a negative 10,000 for present value, is 0 for payment, and then we're going to be solving for future value. So I'm going to leave those values on there, and I'm just going to replace what's on the N in the I over Y key and leave the values on PV and PMT. Since we're solving for future value, it's going to overwrite what's there anyway. So instead of clearing it out and typing those in again, I'm going to save a couple of keystrokes by not clearing it out in this case. So N for this one is 5. We've got 5 total compounding periods. I over Y is 5.1% per year. Present value is that minus 10,000. Payment is 0, and future value is what we're looking for. So I want to overwrite what's on N, and I'm going to do that by pressing the 5 key and then pressing N to store it, and that wrote over what was there before and replaced it with 5. I over Y is 5.1%, so 5.1, and then press I over Y to store it. And now present value and payment are still the same. If I'm unsure about that, I can always check it using the recall key down here. So RCL, recall present value, sure enough it's still 2,000, and then recall payment, and it's still 0. So we've got 4 of the keys entered. We can solve for the 5th by hitting Compute future value, and we're going to have a total of $12,823.71 with investment B. All right, so the question we were trying to answer is, which of these investments offer the higher payout 5 years from now? Investment B with annual compounding periods will give us $12,823.71, and investment A with daily compounding will give $12,840.03. So we're slightly better off by going with investment A, even though the interest rate, the stated interest rate on investment A was lower than the stated interest rate on investment B, and that is precisely because of the more frequent compounding. The more frequently interest is compounding within a year, the more the APR will understate the true effective rate. So we're actually earning a little bit more. These are small differences all around, but it still is more with daily compounding.